Okay, on our fourth 6 weeks test, most of the test will come from the Unit 7 review. 21 out of the 30 questions will come from it. To practice your definitions, you can go to the Quizlet set of flashcards, and you can go through the cards, or you can play the games that are made from the cards. One of the things that we need to add on here is going to be collision theory, and you need to know the tenets or the parts of collision theory. Basically, it says that in order for any chemical reaction to take place, 3 things have to occur. First thing is the particles have to collide. They have to come into contact. They have to collide with enough energy that you can form and break, or you can break and form new bonds. So they have to collide with energy. And then the last thing is that they have to collide in the correct orientation. And what that means is that they're going to come into contact in a certain alignment, and otherwise they're just going to bounce off one another and there won't be a reaction take place. So those are the 3 tenets of collision theory, the 3 things that have to be true in order for a chemical reaction to take place. Okay. Factors that affect the rate of a chemical reaction. There are 3 things we could change and then 1 thing we can add. We can change the temperature. If you increase the temperature, you make something hotter. You're going to make the particles move around more. They're going to move around faster. They're going to come into contact more often, and that means we're going to have a faster chemical reaction. It increases the rate of the chemical reaction. We can also change the concentration. If we increase the concentration, we have a higher concentration. You're going to have more particles in the same amount of space. So that means that you're going to have a faster chemical reaction, more particles colliding with one another. We could also change the particle size. And whenever you change the particle size, what you're ultimately changing is the surface area. And in order to have greater surface area exposed, we need to have a smaller particle size. So the smaller the particle size, the more surface area we have exposed, the more space there is for things to come into contact, and the faster the reaction will be. So those are all 3 things that we could change. Another thing that we could do is we could add a catalyst. The presence of a catalyst does not affect what products are formed. The same products are formed either way, but what it does affect, it increases the rate of the chemical reaction. And the way that it does that is that it lowers the activation energy. It lowers how much energy is required in order to kind of kickstart our chemical reaction, to get the reaction going. So it lowers or decreases the activation energy required. So when we look at our potential energy diagrams, the very top of the curve gets pulled down. It gets lowered. Okay. For the components of a potential energy diagram, we're going to see those on the next page. For our temperature scales, we're going to have the boiling point of water at 212 degrees Fahrenheit, 100 degrees Celsius, and then 373 Kelvin. The way we get Kelvin is we take our temperature in Celsius and we add 273 to it. Okay, the freezing point of water is at 32 degrees Fahrenheit, 0 degrees Celsius, or 273 Kelvin. And then absolute zero is the point where all molecular motion stops. All the particles stop vibrating, and that's going to occur at 0 Kelvin. The Kelvin scale is based off of this idea of absolute zero, and that's going to be at negative 273 degrees Celsius or negative 459 degrees Fahrenheit. If we want to convert between Celsius and Kelvin, you'll need to know that 0 degrees Celsius is equivalent to 273 kelvins. And you'll be given this statement on your test. And so if we want to find the Kelvin temperature, you have to take the temperature in degrees Celsius and add 273. If we want to find degrees Celsius, we're going to have to start with Kelvin and subtract 273. You can look at this example over here and see, well, if I'm at 0, what am I doing to that to get to 273? I'm adding 273. You can also think about the alphabet. It starts with A, B, C, D, E, F, G, blah, blah, blah. So if you're at C and you need to get to K, you have to go forward in the alphabet. You need to add. And if you're at K and you need to get back to C, you just subtract. Okay. You're also going to need to be able to work with our MCAT equation, Q equals MC delta T, where Q is going to be the heat energy. It can be measured in either calories or joules, and joules is our metric unit for measuring heat energy. And the way you find that heat value is by multiplying the other three variables we have. M is going to be mass. It has to be reported in grams. C is our specific heat, and it's particular to whichever substance it is that we're dealing with. And you could find the value in a table or a chart with all those numbers. On your test, I'm going to give you the value that you need to solve the problem. It will have a unit that looks kind of like this. It could be joules per gram degree Celsius. It could be calories per gram degree Celsius. You could have Kelvin instead of degrees Celsius. That's just one example. And then for delta T, remember that little triangle is the Greek letter delta, and it means change. So this is going to be the change in temperature. And the way that we figure that out is we take our final temperature, whatever temperature we end up with, and we subtract the initial temperature, the temperature that we start with. And that's how we find our change in temperature. That's going to help us know whether or not it's going to be positive or negative. And our units that we're going to use are either degrees Celsius or Kelvin. And remember, because of the nature of the two different temperature scales, the difference in one is the same as the difference in the other. So, on the next page, we'll practice a problem using that equation. Okay, if we have a potential energy diagram, we're going to have to be able to identify what type of reaction it is by the shape of it. So if we have an endothermic reaction, think endo, into, and when we have our potential energy diagram, potential energy is going to be found on the y-axis, and the course of the reaction will be going across along the x-axis. So we're going to start out with some reactants with a certain amount of potential energy. And then as the reaction gets started, we're adding energy to it, and it's going to reach a certain point to where we've broken all the bonds and new bonds are going to start to form, and we're going to lose a little bit of energy because of that. And then at the end, our products will kind of level off, and they'll have an average amount of kinetic energy, or potential energy, sorry. So when we look at this, we know it's endothermic because our products have more energy at the end. Our reactants had a certain amount of energy here at the beginning, and then at the end, our products had more. And the amount of energy that we have to add to get up here to the very top, that is the activation energy. So from the reactant line all the way up to the very top, that's the activation energy, the amount of energy we have to add to it to activate it, to get it going. And once it gets up to the very tip top here, this is where we have our activated complex. It's kind of the transition state, the in-between. And then once it loses a little bit of energy, our products will have that total amount. And the difference between the reactants down here and the products up here, that is our delta H. And it's positive because it increased. So that's our heat of reaction. Or another word for that, remember, is going to be enthalpy. So the way we find that again is just finding the difference in those two potential energy values between the reactants and products. Now heat energy went into it. That's our clue. It's endothermic. And since energy is going into it, that means it's leaving its surroundings. And to us, it's going to feel cooler. Okay. So the way that our exothermic reaction diagram will vary, first of all, heat is no longer going into it. Heat is now exiting. And since it is being released, given off, it's going to feel warmer. It feels warmer. The surroundings are absorbing all that heat energy that's being released. And when we have our potential energy diagram, our reactants are going to start out with a little bit more energy here at the beginning than we saw in our endothermic reaction. And we still have to put some energy into it to get it going, but not near as much as we saw in the endothermic. And then as it starts to form more bonds, it's releasing, it's giving off more and more energy until our products here at the end have less than the reactant started with. So we still have an activation energy. We still have that distance. And I'm going to draw this down here. And because this amount of activation energy is less than the endothermic, this is a more spontaneous reaction. It's more likely to occur. And this difference, we started out with our reactants with this much energy, and then we lost that much. That distance is our delta H, our enthalpy, but this time because it's less, it's going to be negative. So you can see just by looking at whether it increases or decreases, we can tell whether or not it's going to be endothermic or exothermic. Now, we add a catalyst to this. We said before that when we add a catalyst, it lowers the amount of activation energy. So what it does is it lowers where the top of this curve is going to be, and so the activation energy required is now going to be less. Okay, so this is what would happen if you added a catalyst to your reaction. And we could have the same thing going on with our exothermic reaction. Now, we don't have to have a diagram to figure out if it's endothermic or exothermic. If we have a thermochemical equation, an equation that's got energy involved in some way, we can figure out if it's endothermic or exothermic just based on which side of our arrow we find that energy value. So our arrow, again, remember, splits this into reactants before the arrow and products after the arrow. So we look and see where our energy is, and our energy is found on the product side. So since it's on the product side, that means that it's being given off, it's being released, it's exothermic, and since it is being given off, it's going to be a negative delta H, and then we just take our number that was in our equation, 72.8 kilojoules per mole. When we look at our next example here, we have our reactants, and we have our products, and we find our heat energy value on the reactant side this time, to the left of the arrow. So that energy is being put into the reaction. It's going to be endothermic, and it's going to be a positive value. Okay. If we want to convert between Kelvin and Celsius, remember if you're starting at K and you want to get back to C, we're going to have to subtract. So we take 273 away, and we're left with 30 degrees Celsius. If we're starting at C and we want to go to K, it means we have to add 273, and we end up with 198 kelvins. For the last one here, we are trying to find out how much heat in joules is going to be required to raise the temperature of 75.0 grams of glass from 24 degrees Celsius to 575 degrees Celsius. So we're going to use Q equals MC delta T. We're trying to find out what Q is. So we need the mass. We have 75.0 grams for the mass. We want to have our specific heat value, so we have to look at our substance. We're dealing with glass. And when you look it up on the chart from your notes, in the joules column, we get a specific heat value of 0.50. And that's in the joules column. So it says joules per gram Kelvin. And remember, we could have it in Kelvin or we could have it in degrees Celsius. It just depends on what other units we have in our problem. So since our temperatures are given to us in degrees Celsius, I'm going to go ahead and put degrees Celsius instead. And then the last thing we need is our change in temperature. So it's going from 24 to 575. So we take our final temperature and we subtract our initial temperature, and that's going to get us 551. That's going to be our change in temperature. Okay. So we have our three numbers side by side. You're just going to multiply those. When we look at our units and see what cancels, we've got grams and grams. We've got degrees Celsius and degrees Celsius. So we're going to be left with joules, which is what we wanted in the problem. And when you type all that into your calculator, we get a value of Q as 20662.5. And we don't actually want all of those numbers. We have to look at the other numbers in the problem and figure out how many significant digits we actually need. And so whenever we look at the 75.0, the 7 and the 5 are definitely significant. The 0 at the end is significant because we have a decimal in the number. Ending zeros are significant when there's a decimal in the number. So that's going to make the 0 at the end of 0.50 significant as well. But the 0 in front is not, because leading zeros at the beginning, are never significant. And then in our last number, the 551, that one's easy. We've got 3 sig figs. So if we have 2 significant digits as our smallest amount, that's what we're going to round our final answer to. So we've got the 2 and the 0, and we look at the 6 to see if it rounds it up. It's either going to say 20,000 or the 6 rounds it up to 21,000. So the 6 is going to make the 20 round up to 21, and we have to keep the right place value, so we have to put 3 zeros at the end. Be sure we put our units. That's going to be joules, and that would be our final answer. If we wanted to change it into kilojoules, remember kilo means 1,000, and so if we divided that by 1,000, we'd get 21 kilojoules. Okay. For the last part here, we have to do a conversion between joules and calories. And on your test, you get a brand new number. So if you messed up in one part, you're not going to get points taken off for the next one just because you didn't get the right answer at the end. So you are going to be given the fact that a calorie is equivalent to 4.18 joules. So you'll be given that on your test. And you'll just start with whatever number they give you in the problem. So we're starting with our 21,000 joules, but we don't want to use our rounded value to do other calculations. We want to go ahead and go back and use our exact value we got in the calculator, and that was in joules. And then we have to set up our equivalency statement here as a conversion factor. So one of those has to go on top and one of them has to go on the bottom. And the way we pick which way it's going to go, we've got our joules unit right here. So that joules unit has to go on the bottom so that they can then cancel out. So our 4.18 joules goes on bottom, our 1 calorie on top. So whenever we do our math, we'll end up with calories. Remember, if it's on top, you multiply. If it's on bottom here, we're going to divide by it. So in your calculator, you're typing in 20662.5 divided by 4.18. And we're going to get a value of 4943.18, on and on. And since our 21,000 was rounded for the correct number of significant digits and it had 2 sig figs, we're actually still going to round this answer to 2 significant digits. So we have the 4 and the 9. We look at the 4 that's beyond that to see if it rounds up. The 4 does not make the 9 round up, so it stays a 4 and a 9. And because that 4 was in the thousand spot, we have to put 2 zeros there. And that makes sense. 4,943 would round to 4,900. And be sure we put our units at the end. That would be calories. Okay. Remember, you also have some questions from your Unit 5 review. 9 out of the 30 questions will come from that, and you'll have to do things like match up the chemical equation to the type of chemical reaction. So you have your addition, decomposition, single replacement, double replacement, and combustion, where the combustion, remember, reacts with oxygen to make CO2 and water, carbon dioxide and water. And you have to be able to identify if an element is diatomic or not. Remember, diatomic means that it comes in pairs naturally. It comes in twos. So we have our high Broncliffe. That's kind of our way to remember what those elements are that come with a 2 after them naturally when they're in pairs by themselves. And you have to be able to look at an equation and figure out the mass of something that's missing. So we have our law of conservation of mass. So we have element A plus element B, and it's going to make that. And if this weighs 50 grams, and this weighs 25 grams, and then this weighs 40 grams, how much does this thing weigh? Remember, our law of conservation of mass tells us that whatever we start with before, we have to end up with the same amount at the end. So we can just kind of put in plus signs and an equal sign, and we just have an algebra problem. We have 50 plus 25 equals 40 plus x. So we have 75 equals 40 plus x. Subtract 40 from each side, and we're left with 35. So we could find out that this is actually going to be 35 grams worth. So we can find out what that missing mass value would be. And then you also have to be able to identify where your reactants are and where your products are. And we already saw up here, reactants are always to the left of our arrow, and products are always to the right of the arrow. And then finally, you'll need to be able to balance a chemical equation. Just add coefficients to the front to make sure you have the same amount of each atom on both sides, the same amount of each element on each side of our chemical reaction.